for the sake of introduction and completeness, say a few words about late Professor Anil Kumar, who, as I think all of you know, was a professor in this department up until about 2002, before his, I would say, quite untimely demise. So Professor Anil Kumar did his PhD in this very department, from this very department, under Professor E.S. Rajagopal. So when I say department, I don't necessarily mean this very building, but what, as some of you would recognize, the old physics building near the central hall, central building. And I think he finished around 1979, and then he was in the US for about 7-8 years, a couple of postdocs in Pittsburgh and UC Santa Clara, before he came back to this department, back to India in this department, and he was there from 1987 up until 2002, when he unfortunately passed away. Because Anil Kumar is quite well known in the area of critical phenomenon in phase transitions. Back in those days, it was really, no, that's okay, no worries. So it's quite well known, in the area of this. And back in those days, early 90s, late 90s, and early 2000, this was a really vibrant and active area, both in our department, of course, but also in the country and across the globe. And he has worked on solids, liquids, looking at re-entrant phase transitions and various different aspects involving this, using mostly electrical measurements, but also light scattering, turbidity, and so on and so forth. So the combination of AC/DC electrical resistivity as well as light scattering and turbidity, and has done some very, very nice work in this area. So we have this memorial lecture honoring him for his contributions to physics and science in the department, in IISc, as of course in the country. So with those few words, I will request Ashish to introduce today's speaker, Professor Jasjeet Bagla. Ashish.
Thank you. So good afternoon, everyone. Hope all of you by now know me. I'm Ashish. And it's a great pleasure for me to introduce Jasjeet, Professor Jasjeet Singh Bagla from IISER Mohali. And finally, I have this pleasure to introduce Jasjeet, because Jasjeet was also my PhD guide. So Jasjeet did his PhD from IUCAA from 1992 to 1996, primarily focusing on cosmological n-body simulations, structure formation. After that, Jasjeet moved on to Institute of Astronomy, Cambridge, for a postdoc from 1996 to 1998, and had another postdoc at CFA Harvard for 1 year. And after that, Jasjeet joined HRI in 1999. And from 1999 till 2010, Jasjeet was at HRI. And in 2010, Jasjeet moved to IISER Mohali as a professor. And since then, Jasjeet is Jasjeet is at IISER Mohali. So Jasjeet has worked on a broad set of problems in both astrophysics and cosmology. So I'm not going to go through all of them. I'm just going to highlight 3 of them. So Jasjeet primarily, for example, in his thesis and during his postdoc and during HRI, worked a lot in cosmological n-body simulations, primarily focusing on algorithms and try to improve the cache memory management in the these n-body simulations. In addition, Jasjeet also worked a lot in gravitational lensing with me. That was my thesis. In addition, the final thing is Jasjeet worked a lot on dark energy also, while he was in HRI and while here he's in IISER Mohali. So for example, different parameterizations of dark energy. Some of you may know Bagla, Padnavan parameterization. Yeah, so I would say these are the main things that I would like to highlight. There are many more things that I can talk about, but in the interest of time, I would call Jasjeet. Today, Jasjeet will talk about dark energy and what we can find out about dark energy. Thanks, Jasjeet.
Thank you, Ashish, for the kind introduction, and to Physics IISc for the invitation. I'm honored to be giving the Anil Kumar Memorial Lecture today. I will be talking to you about dark energy, and this is at least the first part of the talk is going to be a very broad historical introduction as to how the field has developed, and then I will talk about some of the open questions which are there. Now, unfortunately, so cosmological constant, which is the older name for dark energy, one of the models for dark energy, was first introduced by Einstein in 1915 when he wanted to construct a static model of the universe. And in his general theory of relativity, he found that he could not do it with normal matter only. So he plugged in a term which he thought he could sneak into Einstein equations, and this is something which he regretted later on, much later, because he had listened to an astronomer while making that decision. The astronomers had told him that the universe seems to be static, and he abandoned the natural expanding model solutions which he was getting in his theory in order to produce a static model. And in 1928, Robertson derived the time-dependent version of what we call the de Sitter solution, and he showed that this gives you accelerated expansion. This particular paper by Robertson in 1928 is very fascinating because he talks about thinking of the de Sitter solution as providing a background and as galaxies being test particles in this expanding background. And then he wants to know what observers will see. He realizes that we are talking about curved space-time, which means that I cannot just take velocity of one observer and another observer and subtract. So he embeds this curved space-time in a higher dimensional flat space-time, does the transport, finds the relationship. He found that typically observers will see each other going away from each other, and he took the nearby approximation, found Hubble's law, and in a footnote, using Hubble's data and Schleifer's data, he gives the value of Hubble's constant, which you get by fitting. He also asked whether presence of mass, because galaxies are fairly heavy, will alter the large-scale metric, and he essentially combined the Schwarzschild and de Sitter to demonstrate that you can have a Schwarzschild-like metric around a stable source, but at large scales it will go over to de Sitter, which is expanding. So that was an interesting solution. Robertson, of course, realized that by using the de Sitter model, he had underplayed the role of normal matter. There was something in the space-time which was causing it to expand, but that had nothing to do with the matter in galaxies. And of course, Lemaitre had in 1927 derived a much larger class of models, expanding models, and unfortunately, when Lemaitre's paper was translated to English from Belgian, the para about expansion and Hubble's law was omitted. So interesting things were happening around that time. But one thing which we need to take home is that the early estimations of Hubble's constant were very wrong. They were wrong by about an order of magnitude, overestimating the Hubble's constant. And because the age of the universe is of order inverse of Hubble's constant, the expected age of the universe was thought to be of the order of 1 billion years, not 10 billion years. And as a result, it was directly in conflict with many observations, including oldest rocks on the Earth. And this created a problem. So people tried fudging around it, because by adding a cosmological constant, you could increase the age of the universe. And of course, other people came up with more creative solutions like the steady state model. And this continued for about 20 odd years before the problems with the estimation of Hubble's constant were fixed. Part of it was related with extinction by dust. Part of it was related to misidentification of nebulae in nearby galaxies as individual stars. So therefore, the brightness was mistakenly attributed, much higher brightness was attributed. By mid-1950s, part of the errors in Hubble's constant had been sorted out, but there was still a tension between the oldest objects which we see, or at least we thought we saw, and the estimated age of the universe. So this is the kind of very early development in terms of cosmological constant. It's interesting to note that determination of the Hubble's constant started to converge in late 1970s. So first measurements, reasonably good measurements, giving numbers around the current number which we have, which is of order 70 kilometers per second per megaparsec. That came out in late 1970s. But different groups kept on taking observations, making measurements, and claiming that they were getting values anywhere between 40 to 50 kilometers per second per megaparsec, all the way to 110 kilometers per second per megaparsec. So that kind of fight continued well into 1990s, as we will see. So this is one of the first efforts to try and understand what parameters describe our universe. This is from 1974. Richard Gott, James Gunn, David Schramm, and Beatrice Tinsley. And what they did was essentially they did a census of what we see in the universe and asked what is the total content of the universe. In case of an expanding universe in Einstein's theory of relativity, we can naturally describe a particular scale density called the critical density. If the overall density in the universe is equal to the critical density, then the space is flat. If it is less, it is open. If it is more, then it is closed. So what they found was that the density of everything which they could see is no more than 1/10 of the value required for closure. So they argued that the density parameter of the universe was of the order of 1/10, and the paper goes on to discuss various possibilities, but they essentially said that unless there is some kind of a uniform and dark medium pervading the universe, this is what they get. But after publishing the paper, they realized that if this is indeed to be the correct model, then again you run into the difficulty with the ages of oldest objects which you see. The oldest stars which we see in the universe are around 12 to 13 years old. And if the Hubble's constant is to be somewhere around 60, 70 kilometers per second, and it only contains about 1/10 of critical density and nothing else, then the age of the universe will turn out to be around 9 to 10 billion years. And that is a problem. So a year later, Jim Gunn and Beatrice Tinsley, they did analysis of a wider class of models, and they argued that we need a positive cosmological constant. Otherwise, we are unable to satisfy the ages of the oldest stars which we see in our galaxy. Interestingly, Beatrice Tinsley, who is there in this paper as well as the previous one, had the distinction of introducing Alan Sandage for a colloquium where she introduced him and then said everything he's going to say is wrong. Because Alan Sandage had been trying to measure cosmological parameters, assuming that galaxies are somewhat standardized objects. And Beatrice Tinsley was the first one to show that chemical evolution of galaxies and stellar evolution in galaxies happens at the same time scales over which you are doing these observations, and therefore you cannot take galaxies to be standardized objects. So she is essentially the person who introduced the idea of evolution of galaxies and chemical evolution of galaxies in astronomy. Unfortunately, she died too early. So this is early to mid 1970s, but at the end of 1970s, the idea of inflation caught up everyone's imagination. The problems had been in discussion within the cosmology community, and even if we go back and read discussions from Einstein's centenary, where it was pointed out that, yes, we see a universe which looks like a smooth, homogeneous, and isotropic universe. CMBR had been detected many, many years ago, and it was seen to be highly isotropic. And the problems which were highlighted in those discussions were the horizon and the flatness problem. Why is the CMB temperature in opposing directions the same? Because if we follow the then standard cosmological model, these two regions would not have been in causal contact at the time when CMBR photons started their journey. And why is the space so close to being flat? And Starobinsky and Guth came up with an astroparticle motivated solution where highly accelerated expansion in very, very early universe gives rise to a universe which should be close to flat and which should not have the horizon problem because of this early accelerated expansion. And another major prediction of the inflationary paradigm was the presence of density fluctuations at very large scales. And this was verified by Kobe in 1992 and subsequent probes. But this paradigm essentially became like a religion, and most theoretical cosmologists started thinking of the Einstein de Sitter model, where the density of matter, non-relativistic matter in space, is equal to the critical density, because that is what they thought inflation pushes you towards by solving the flatness problem, to the extent that they started ignoring observations. If you go and talk to cosmologists who were analyzing observations during late 1980s, early 1990s, you will come across anecdotes where papers were rejected on the grounds that who cares about observations, inflation tells you that omega matter is 1. So there is a lesson in there. One should respect observations seriously. So one of the first things to be taken seriously in the cosmological community was the measurement of galaxy correlation function in APM galaxy survey. APM stands for automated plate measurement. So in Cambridge, they had set up this digitizing of old plates of the sky taken using the Schmidt telescope in Australia. And they had software at the back end which could distinguish between stars and galaxies. So they made this automated catalog of galaxies over roughly 1/3 of the sky. And then they went on to measure the galaxy correlation function. The correlation function which they measured broadly follows these points over there. And if they assumed an Einstein de Sitter universe, they should have fallen on this dotted line over here. Okay. The reason is that in the inflationary paradigm, when you create fluctuations at all scales, after inflation ends and the universe goes into a decelerated expansion mode, gradually different length scales enter the Hubble radius, and scales which enter the Hubble radius early on during the radiation dominated era, their growth is stunted. So at small scales, you have stunting of clustering. So this is essentially because of nonlinear clustering. But at small scales, you have stunting, and at large scales, you have a variation, mainly because at very, very large scales, the growth has, those modes had not entered. And the transition scale, which corresponds to the scale over here, is essentially the Hubble radius at the time when matter and radiation contributed equally to the energy density. So if there is less matter, this happens at a later stage and therefore happens at a larger scale. So that was the transition scale, and they argued that the omega equal to 1 CDM model does not fit at all. So either you need an open model or a model with cosmological constant, and they noted that the open model will run into difficulties with the age of the universe. So this was 1990. The next important finding, now this interestingly is very, very similar to what Gott, Gunn, Schramm and Tinsley did in 1974, was trying to do a budgeting of the contents of galaxy clusters. And these people focused on one particular nearby cluster, the Coma cluster of galaxies. And they argued that no matter how you calculate the overall matter contribution from clusters of galaxies falls well below the expectations from Einstein-de Sitter. Therefore, Einstein-de Sitter cannot be the correct model. But notice that the abstract kind of hedges the bets, not hedges the bets, but puts it very, very mildly, because the inflationary paradigm was still very, very strongly rooted, and people still believed very strongly that the Einstein-de Sitter model is the correct one. And then in 1994, Peter Coles and George Ellis, they put together data on a large number of clusters of galaxies and other observations, again doing similar work, but different data set, and they argued that there is a case for an open universe. So this was a review article, and they published a review article after trying to publish their research for many, many years, failing to get the papers across, ultimately publishing their research in a book, and then getting an invitation to publish a review article. So this is how strong dogma can be in science at times. Then in 1995, Oestreicher and Steinhardt, they did this interesting study of different constraints. So they looked at constraints from Big Bang nucleosynthesis, they looked at gas in clusters, and they looked at the large-scale structure, essentially the shape of the correlation function for galaxies, and ages of different things. Unfortunately, it's a very busy plot where they have mixed up different kinds of models. But essentially, they argued that the age of the universe has to be more than 11.5 gigayears. Then this is essentially the parameter space that is left to you. This is the Hubble parameter. Notice that the allowed regions are between 50-something going up to 80-something. The scale goes from 0 to 1. And this is the density parameter, and they are getting numbers between 0.2 something going up to about 0.4. So unaware of that work, we also did something, and interesting side story. Professor Narlikar reviewed the 1975 paper by Gunn and Tinsley in the IUCAA NCRA Journal Club and challenged younger cosmologists that can you repeat the analysis today. So I took the bait and I did these calculations. So the constraints were similar to what Ostreicher-Steinhardt had used. The plot is slightly different. So on the x-axis is again the, no, on x-axis over here is the density parameter. On the y-axis is the Hubble parameter in units of 100 kilometers per second. We have constraints coming from ages. So points lying below this line mean that the age of the universe is more than 12 gigayears. This is 15 gigayears. This is 18 gigayears. These curves are coming from shape of the correlation function. And then we have other constraints coming from nucleosynthesis. There is this curve over here which comes from damped Lyman alpha systems observed at high redshift and so on. And when we combine all of that, we don't find any region which is permitted. So these are open models, no cosmological constant. We find no region which is permitted at 1 sigma confidence level. At 2 sigma, we have this particular region. If we include cosmological constant, then we have a much wider region. Again, the same set of observations, plus you see one more over here. This is from the high redshift supernova project, as was available in late 1995. And according to them, the allowed region was to the right of this line. Okay. So we chose to discard this particular observation, saying that it is still very preliminary. At that stage, they only had 7 intermediate redshift supernovae. And they predicted the value of cosmological constant to be less than 0.33 at that time. So if we had taken this seriously, essentially the only allowed region would have been this one. And with cosmological constant, because the age constraint is lightened, we could have a much larger parameter range, with this being permitted at 1 sigma level. Okay. Omega matter. So you will see that this region is around omega matter of 0.5. And the main reason for that is that we are looking at the line below 15 gigayears. So at that stage, the estimate of ages of globular clusters was that they could be at least 15 gigayears old. If you go lower, like if you want to look at the current values, 13.8, 13 gigayears or so, you will come over here. So you will shift to smaller values. Oh, the precursors of the observations like this one. See, the first one which I showed, 1974, this one. This is 1974, which says that omega, counting everything which we see, galaxies, clusters, etc., is less than 0.1, not more than 0.1. And these continued to be the case. You know, it kind of went up slightly to about 0.15, 0.2, but not more than that. But that was completely ignored. It would have been faster, but then they would, I think the main issue was with theoreticians, because they felt that having a non-zero cosmological constant, but a small cosmological constant, much smaller than what the particle physics theories predict, will land them in trouble. So they were happier thinking that maybe supersymmetric theories are right, lambda will turn out to be 0. But then if you want to solve the flatness problem, omega has to be 1, it all has to be matter. The estimation of mass of clusters includes any dark matter which is there in clusters, similarly for galaxies. Then of course in 1998, the first supernovae around redshift of 1 were discovered, and the supernova cosmology project shifted its preferred values from around omega of 1, omega matter of 1, to models where cosmological constant of 0 is simply not permitted. So this is the band for the middle redshift supernovae which were present in the earlier analysis, and this is the band for 0.83. You get the intersection which is over here. Okay. So you need an omega lambda. Look at the scale though. Okay. So you need an omega lambda over here. And then a couple of years later, measurement of a peak in the temperature and isotropy angular power spectrum of CMBR was made using balloon-borne experiments. So this is a peak, the first big peak which appears in the CMBR anisotropy spectrum. And the location of that peak is very sensitive to the total content, matter content of the universe. And this is the likelihood. And you can see that the likelihood peaks at omega of 1. So now we had observations telling us that omega matter is only around 0.3, 0.2 to 0.4, and total omega is around 1, and that we have an accelerated expansion. So all of this combined essentially told us that we are living in a flat universe which contains cosmological constant, and this established the lambda CDM model as the standard cosmological model. And there is very little evidence of non-zero curvature. So these are some of the latest constraints coming from the telescope, the various other observations. You can see that this dashed diagonal line is the flat universe, and you have daisy observations of baryon acoustic oscillations. You have the supernova observations, and you have the ACT and Planck observations over here. So you end up with a intersection somewhere near a flat universe. So if you look at the contours for curvature, the preferred value is very, very close to 0. So this line is for 0. And all observations are consistent with curvature 0. But even if it is there, it's extremely small. Now, coming back to models for dark energy, the initial response was, of course, to assume a cosmological constant. But then we know that cosmological constant has a fine-tuning problem. If we look at the unified theories, the predictions from there give you an omega lambda which is more than 100 orders of magnitude off from what we observe. And many attempts, therefore, have been made to develop models that generate dark energy in a dynamic fashion. However, once you start looking at these closely, you find that each of them involves some amount of fine-tuning as well. Many other approaches have also been tried, for example, modified theories of gravity. But slowly, as work goes on, people have shown that many of these, what looks like very disparate approaches, are actually equivalent. For example, Dipayan Mukherjee, who is currently at RRI, and Arvinder Jassal and Kinjar Klochan at IISER Mohali, they showed that the quintessence scalar field-based model for dark energy and FFR modified gravity models are equivalent. It is just a change of frame, going from Einstein frame to Jordan frame. A large number of phenomenological models have been proposed with no basis in any fundamental theory. It's essentially a fitting exercise. Initially, it was all right, you wanted to try simple things like Taylor expansion and so on, but those have started to run when we are way past the stage when they have any serious utility. And the question is, how can we figure out which model of dark energy is the correct one? So ultimately, that would be our quest. We want to find what is the correct model of dark energy. Now, key observational constraints arise from expansion history of the universe. So high redshift supernovae of type 1a, they have peak magnitude which can be standardized, and therefore you can measure luminosity distances as a function of redshift. Acoustic oscillation scale in measurements of galaxy clustering is a specific scale. When you measure galaxy clustering, you find something sticks out. If you do the correlation function, you have a peak near 100 megaparsecs. If you look at the power spectrum, it has oscillatory features in the galaxy power spectrum at corresponding scales. And those scales, because we are viewing them in angle in the sky, they give us the angular diameter distance as a function of redshift. And there are somewhat weaker constraints coming from Hubble parameter estimations at different redshifts. So all of these effectively constrain the scale factor A of t. So that's the function which you are trying to constrain. And it was pointed out back in 2002 by Padmanabhan that any field-based model can be tuned by choosing an appropriate potential. And you can actually invert the problem. Given any scale factor, you can find out which potential will give you this expansion. Therefore, since you can do that for any field-based model, you really cannot tell the difference between different classes of models based on just the expansion history. So these observations cannot distinguish between different classes of dark energy models. The question which arises is, can observations of clustering help in any way? Can they break the degeneracy? So this is the question with which we started. Some of the early work was done using relativistic perturbation theory. And it was shown that growth of fluctuations in dark energy is strongly suppressed at small scales, which means at smaller scales dark energy is pretty much smooth. Although the perturbations in dark energy can be significant, even comparable with matter fluctuations at very, very large scales. No, these are perturbative in the gravitational potential. So essentially metric coefficients. Because you have Friedman-Robertson-Walker metric describing the background. Now you say that instead of a smooth universe, I have perturbations around it. Okay. Yeah. So you perturb the metric coefficients and work with that. Several attempts have been made to construct Newtonian models of spherical collapse, assuming that dark energy is homogeneous at small scales. So one is Maurer and Lahav, then Pace, Weisman, Buttleman, and Devi and Sen, 2011. Some of these also tried to, for the smooth dark energy, they essentially appealed to the perturbative results, saying that at small scales dark energy is anyway not clustering, so let me assume that it is smooth. But some of them also conjecture as to what will happen if dark energy could cluster at very, very small scales. Yeah, so here in the perturbation, what we find, what is found is that dark energy perturbations can be significant at around the Hubble radius or larger, not at very small scales. And several authors attempted to model growth of perturbations in spherical collapse by assuming a fluid kind of a representation. So here, the main difficulty is that if you take a barotropic fluid, then the equation of state parameter and the speed of sound are related. So they had to break that. They had to assume two parameters describing the fluid, where the speed of sound becomes independent of the equation of state parameter. But then it becomes a two-parameter problem, and mapping it to any ab initio theory becomes harder. People also did linear growth studies using similar models. So what we wanted to do was to look at least something which I can relate to fields, which may be a better description of the whole thing. So we decided to look at nonlinear spherical perturbations in quintessence models of dark energy. And what we did was to do a self-consistent relativistic study of matter and dark energy. I'll show the equations in a brief while. The evolution of dark matter density contrast as well as turnaround radius and virialization we found are unaffected by dark energy perturbations. So this in some sense is consistent with the perturbative results that dark energy does not seem to cluster much. dark energy perturbations remains small at all scales and at all times. So we were studying smaller scales. So this statement essentially is in respect to that. And the equation of state parameter W becomes a function of space, but again, variations in that are very, very tiny. The effects of dark energy clustering are most pronounced in voids, though these effects are also relatively small. And they are more pronounced in voids because in voids, matter becomes more and more underdense, and dark energy essentially becomes the dominant field, dominant medium over there. So what had we done to get here? What we did was to assume a Tolman-Bondi spacetime, spherically symmetric. So we had two metric coefficients which were left as free functions, B and R. And we had non-relativistic matter in shells which could move around. And we chose initial conditions to match an Friedman-Lemaitre-Robertson-Walker model at large scales, which means that any density perturbations which we simulated were compensated so that net density contrast at large scales was 0. And metric coefficients, matter, and scalar field, they were solved self-consistently using this bunch of equations. The evolution for the scalar field inside the virial radius has to be approximate because we essentially have to halt these shells at some stage. So we have the metric, the equations for the two metric parameters, equation for the scalar field, and the continuity equation for the matter part. So this is the study which we did to get to the results which I mentioned briefly. So then we wanted to know that, okay, these are the results which we are getting for quintessence. Now, if I change the model, what will happen? So I should study it with two different field-based models. But we needed to work with models tuned so that the expansion history is identical in two classes. Okay? So we had to set up a numerical experiment along those lines. And then a comparison will tell us whether there are any observables that can distinguish between the two classes. So we chose to work with the quintessence and tachyon class of models. The tachyon class of models has an action which is inspired by string solutions, low energy string solutions. But before we got there, we had to do a reconstruction of potentials in these two cases to ensure that we get the same expansion history. So it turns out that if we have a constant W kind of an expansion history, then for tachyons, we have a parameterized solution. V in terms of scale factor and phi in terms of scale factor. And combined, this gives me V of phi. And for quintessence, it is more straightforward. I have a solution for V of phi. Of course, here it's not only parameterized, I also have this hypergeometric function sitting here. But in general, we showed that we can find a numerical solution for V of phi in either class of models. So we proceeded to work with these and then did a comparison between the tachyon action and quintessence action. This is for an underdense region. So this is delta dark matter as a function of scale. So we had a void compensated by an overdensity at the periphery of the void, and then it goes to no density contrast beyond that. The curves here are for constant W. The lines are for tachyon models, and the points of different types are for the corresponding quintessence models. The line over here, this one, is for so this is for tachyon corresponding to W of minus 0.5. And then we have for minus 0.9 and minus 0.975. And we find that there is really no significant difference in these. Okay. The plots over here are for a model where the equation of state parameter varies linearly with scale factor. It either approaches lambda CDM or it goes away from lambda CDM. The present value of the equation of state parameter is taken to be minus 0.9. And you can see that there are two lines and two sets of points, and they match perfectly. Okay. So we have no distinguishing feature over here for the two different classes of models. Then we looked at the turnaround radius in units of initial radius of the perturbation. So this is supposed to be a quantifier of the dark energy models, and this is also related to observables. Observers often call it the splashback radius. And we find that for the two CPL models, the tailored expansion models for W, the tachyon and quintessence models sit right on top of each other. There is absolutely no signature in dark matter clustering, which is coming from dark energy. Same for dark matter overdensity at turnaround. Similarly, we have the ratio of the virial radius to turnaround radius and the dark matter density inside a virialized halo. Nothing. So the clustering of dark energy is not leaving any signature in clustering of dark matter. So dark matter clustering is what we observe, and we will find no signature over there. If we look at dark energy perturbations, not directly observable, but we may be able to find some linkage. In that case, we find that, so this is constant W, these two. This is the density contrast in dark energy, and this is the variation in the equation of state parameter for dark energy. And we can see that for minus 0.975 and for minus 0.9, the tachyon and quintessence curves match. For minus 0.5, they sit quite apart from each other. See that overall amplitude is small, but I see a difference. Okay. So the dark energy carries a signature of the class, but dark matter does not. And similarly, in the equation of state parameter also, I see that if W is like minus 0.5, then I can make out some difference, otherwise I cannot. When we look at CPL, which is the linear expansion, linear variation, there are differences, but they are very, very tiny. Overall, the scale itself is very compressed, but the differences are extraordinarily small to make any dent in observables. So we were wondering as to what is going on and how can it be so disappointing in some sense that we will not be able to tell what is the correct model. We thought that we'll fall back now on perturbation theory, because in perturbation theory the equations are simpler and we may be able to do some comparative analysis. So this is the work which we took up later, and we did, no, this is still the, yeah. So when we did this, we were able to show that we can, at the perturbative level, we can use an interesting set of variables to simplify the equations for the two field models and write them in the same language, which makes the comparison easy. So these are recasting the equations in different variables, and this is for tachyons, this is for quintessence, and you will notice that the full tachyon equation and the first two lines in the quintessence, they are identical. This is the difference. But this bracket has a prefactor omega, which is actually 1 plus W. So if W is close to minus 1, this effectively becomes a second order. So this gave us some insight into what was going on. We were essentially, our universe has W which stays close to minus 1 throughout. And in that scenario, the differences are expected to be extraordinarily small. But then we went on to ask whether there are any signatures at very large scales where dark energy perturbations are probably significant. And we found that indeed at scales which are of the order of 2000 megaparsecs upwards, there are differences. The differences are still small in the sense that the biggest differences are for 2000 megaparsecs, where it still stays well below 10%. And I have no way of directly measuring density contrast of dark energy. Okay? So I have to measure it via something. And we think that the integrated Sachs-Wolf effect could be the only route. So this is photons coming from CMBR up to us. Because the overall potential is evolving, it will leave an integrated signature. That signature, because it is related with variation of potential, is correlated with the galaxy distribution at the intermediate redshifts. So by cross-correlating CMB anisotropies with galaxy distribution at redshifts around 1 to 2, one can detect this effect. So this effect has been detected. But even the detections of integrated Sachs-Wolf effect are not very high significance as of now. And we are looking for a very small difference between two models, which will show up. So the best case at a particular scale, it's of the order of 3 to 4%. So certainly out of bounds for the present observations. Maybe in a couple of decades, one can find something if one is lucky. So the present status of the field is that a number of codes have now been developed to study clustering of dark matter and dark energy together. These include some N-body codes which work with metric perturbations. So seeing our work and other work, they have realized that since at small scales, dark energy clustering is not very important, they can treat dark energy at a linear perturbation level. Although we have shown that there are corrections to that which happen by looking around cluster size halos. So they work with metric perturbations and approaches which are based on effective field theories of dark energy. So these two are for Hoddersky theory specifically. And it's just come out last week. And these can be used to study evolution of perturbations in a generic setting without a recourse to highly symmetric collapse at revolution. So maybe these studies will lead to something interesting. The most realistic models that we have, which fit other observations, they lead to no impact of dark energy on matter clustering over and above the effect through expansion history. So we are essentially back to square one as of now. This is just the summary. The dominant impact of dark energy on observables related to matter clustering is through the expansion history. And imprints of the class of dark energy model appear to be subdominant if expansion history is close to lambda CDM. And characteristics of voids may hold a promise, primarily due to larger scales and dark energy dominating in these. This needs to be investigated further. And a significant improvement in ISW effect measurements may help in differentiating between classes of dark energy models. So I didn't show those plots. We did look at what Planck and other contemporary instruments can do, and they have zero discriminating power as of now. One can parameterize the different term, the term which is different between these two models, and essentially the current and upcoming surveys can do absolutely nothing over there. On the positive side, going by Monty Python's always look on the bright side of life, we can use this relative insensitivity to work with whatever is the convenient model. Whatever makes my calculations easier, I can use that because I know that dark energy clustering is not making a big difference over here. I'll stop here. Thank you. It's very sensitive to what is the ratio of omega matter to omega CMB. So if you have, so for an open universe or a lambda CDM universe with the same omega matter, it will be at the same scale. No, no. No, no. So what we can do is the following. You give me an action and you give me an expansion history. For a smooth universe, I can construct the potential which will give me this expansion history for this action. That I can do, that is unique. Okay, that is what we have done. So that is what we have done for the two classes of actions. Now if you say that you also want to include clustering, for clustering you may need to add other things depending on what is the interaction within that sector or across two sectors. That you may have to do. So right now what we have assumed is minimal coupling, which means that any clustering which is happening is purely due to gravitation. No. So we don't foresee anything obvious. As I said, the characteristics of voids, lensing around voids, which will be weak lensing, that may hold a promise, but that needs to be looked at a little bit carefully. We have not done that yet. I think Rajiv had a question. Yeah. Anand.
Finished.
Yeah.
Can we have a consistent way? Can we have a consistent way of looking at particle physics models and simultaneously trying to have reasonable candidates for dark energy, and have these two, you know, the particle physics sector and the cosmological sector go hand in hand and constrain each
So
other?
I'm not aware of any model where this has been worked out properly, but it will be great if it can be done. The main challenge is that the energy scale of dark energy which we are witnessing is so low that it will probably have to come through some cancellations and corrections which nobody has produced yet. That seems to be the main challenge, because the expected scale is very, very different.
Only for these two specific models that you have looked at, right?
Right. So for these two, I don't know if there is a
but
difference.
this is still not the most generic statement
No.
that one can draw,
No, no.
right? Given that there are like, infinite number of dark energy models. So, but can you think of a way where this could be made more concrete and more robust statement?
Okay, so I did not talk about that aspect, but the difference term which we have in linear theory, this term. So we computed this for a few other classes of dark energy models like KSNs and so on. And we asked whether there is any way in which this could turn out to be significant.
Yeah.
So we did not find any obvious example.
I see.
So the thing to do would be, since this is proving to be a nice template for comparison, if you take a theory, you essentially recast things in perturbative regime into this language and ask what are the different terms. So that, I think, would be a way forward. But looking at field-based models, not modifying gravity, we thought that tachyon and canonical scalar field were about as far apart as you could easily get.
The second question was that Of course, you know that there are these two diagnostics or even more diagnostics which have been proposed by Sahani and Shafilu and all those people, but at the background level,
Yes.
at the expansion history level.
Yes.
Can one do something for the perturbative level, which could perhaps be more useful if you want to distinguish multiple dark energy models?
No, I think essentially recasting in this language.
So
we could
identifying
think
which
of-
term will affect your perturbations and
Right.
recasting them in terms of some diagnostics
Right. So there are,
might be.
in this language, actually there are multiple equations which describe the system,
Mhm.
but the other equations which are there don't contain any reference to the potential
Okay.
or the field. Okay. So we thought that there we will not get any difference at all. It is only this particular equation that has a difference. Yeah, but this could be a way of parameterizing that.
Yeah, very fascinating talk. So mine will be a very naive one at the end of this, and I think some high tea is awaiting. So you expect clustering, or people expect a clustering of dark energy because dark matter, because matter, as we see, is clustered. Is that the
Now for dark
the reason, or there is some other more fundamental reason as to why it should be clustered at any
for
scales?
dark matter, even though we don't know exactly what it is, we can say with great degree of confidence that it is very weakly interacting other than gravitationally, and that it is non-relativistic at present. So with these two, given initial density fluctuations, we know that dark matter will cluster.
Okay.
Dark energy, if it is not the cosmological constant, in that case, by equivalence principle, it has to cluster.
Okay.
Amplitude may be small, but it has to cluster.
Okay.
Otherwise, it will violate various things.
Okay. So I guess the question of the contrast in the fluctuation, the cluster.
So the
That's the challenge probably.
Yeah. So the challenge, the question which we were asking ourselves was, can I look at galaxy clustering and somehow tell the difference between two different classes of dark energy models because they cluster slightly differently? That answer, unfortunately, turned out to be no, if our determination of the expansion history is correct.
Okay. Thanks.
Any other questions? Okay, so let's thank our speaker once again.